A major industrial fire at the Viva Corio refinery in Geelong has drawn national attention after thick black smoke was seen for miles and emergency crews rushed to contain the blaze. The refinery is one of the most important fuel processing facilities in the region, supplying a large portion of gasoline, diesel, and jet fuel. The incident raised urgent questions about what triggered the fire, how it spread, whether safety systems worked, and what the long-term consequences might be. This video explains the event using verified industrial knowledge, realistic refinery operations, and careful analysis while avoiding speculation presented as fact. What happened at the refinery? A fire broke out inside the refinery complex, producing a large smoke plume visible across surrounding areas. Emergency services responded quickly and began containment operations. Parts of the facility were isolated as a precaution, and safety protocols were activated to prevent further escalation. Authorities confirmed the situation was serious but controlled. Where the fire likely started. Refinery fires typically begin in processing units where hydrocarbons are heated, pumped, or separated. These include distillation columns, pipe racks, pumps, heat exchangers, and storage transfer lines. The most common scenario involves a leak of flammable vapor or liquid that finds an ignition source such as hot equipment, static electricity, or rotating machinery. What the operational environment looked like before ignition. Before a refinery fire, systems are normally operating under high temperature and pressure. Crude oil is heated and separated into components such as gasoline, diesel, and kerosene. Pumps circulate fuel continuously and valves regulate flow. Any small deviation in temperature, pressure, or flow can create a hazardous condition if not corrected quickly. How a small anomaly can become a major fire. A minor cooling issue or pressure imbalance can allow temperature to rise inside equipment. This can increase vapor formation and stress on seals and joints. If a seal fails or a flange loosens, hydrocarbons may escape. Once released into the air, vapor can travel and ignite instantly if it meets a hot surface or spark. What happens during the first seconds of ignition? When vapor ignites, the flame spreads rapidly through the cloud. This can appear as a sudden flash followed by sustained fire. If nearby pipes contain fuel, heat from the initial flame can weaken them and cause additional leaks. This creates a chain reaction that expands the fire zone. Why thick smoke was seen for miles. Refinery fires produce dense smoke because burning hydrocarbons release carbon particles and unburned fuel droplets. When heavy fuels such as crude oil or diesel burn, smoke becomes darker and more visible. Wind can carry this plume over long distances, making the fire appear larger than the actual burn area. How heat affects refinery structures. Steel structures lose strength when exposed to high temperatures. As heat builds, support beams begin to soften and expand. Pipe racks may bend, platforms may sag, and insulation may burn away. Engineers design refineries to withstand heat, but prolonged fire exposure can still weaken structural components. Whether there was a structural collapse. Large refinery fires sometimes cause partial collapse of pipe racks or walkways. This happens when steel weakens and cannot support the weight of pipes filled with fuel. Collapse can also break additional lines, increasing the fire intensity. Investigators usually examine debris patterns to determine whether collapse occurred early or later. Why suppression systems do not always stop fires immediately. Refineries use foam systems, water deluge cooling, and emergency shutdown valves. These systems are designed to control fire spread rather than instantly extinguish it. Foam must be directed to specific areas, and water is often used to cool equipment to prevent explosions. Manual firefighter intervention is still essential. What could delay automatic safety response? Automatic systems rely on sensors detecting heat, flame, or pressure changes. If a fire begins outside sensor coverage or grows rapidly, systems may activate seconds later. In high-risk environments, even a short delay allows flames to expand across connected piping. How investigators reconstruct the ignition sequence. Experts examine burn patterns, melted metal direction, and damaged equipment. The deepest burn area often indicates the origin. They also review pressure logs, temperature data, and alarm records to determine what changed first. What role hydrocarbons play in fire intensity. Refineries handle volatile fuels that vaporize easily. Gasoline vapors ignite quickly and burn fast, while heavier oils burn longer and create thicker smoke. When both are present, fires become both explosive and sustained. Whether an explosion occurred, some refinery fires include pressure bursts that sound like explosions. These may come from vessels venting, pipes rupturing, or safety valves releasing. Not every loud blast is a major explosion, sometimes it is controlled pressure release. How emergency shutdown works. Operators isolate fuel supply lines and depressurize units. This reduces the amount of fuel feeding the fire. Flaring systems may burn excess gas safely to prevent buildup. This controlled burning can create tall flames visible from far away. Impact on fuel supply. If a refinery unit shuts down, fuel production drops. This can affect gasoline and diesel availability. Authorities often increase imports or use reserves to stabilize supply while repairs are made. Environmental concerns. Smoke from refinery fires contains soot and combustion gases. Air quality advisories may be issued. Monitoring teams measure particles and gases to ensure community safety. Worker safety during refinery fires. Refineries have evacuation routes and muster points. Personnel move to safe zones while emergency teams isolate the affected unit. Safety training focuses on rapid evacuation and communication. How long investigations typically take. Industrial fire investigations often require detailed inspection and data analysis. Engineers review logs, interview staff, and examine damaged equipment. Final reports can take weeks before the exact cause is confirmed. What this incident means for industrial safety. Refinery fires highlight the importance of maintenance, sensor reliability, and emergency response. Facilities often review inspection schedules and upgrade monitoring systems after such events. Why aging infrastructure is a concern. Older equipment may experience fatigue, corrosion, or outdated control systems. Modern upgrades improve detection speed and reduce failure risk. Many refineries gradually replace critical components to improve safety. Key lesson from the Geelong Refinery fire. Even small leaks in high-temperature fuel systems can escalate rapidly. Early detection, strong maintenance, and effective shutdown procedures are essential to prevent large-scale incidents. Finally, the Geelong Refinery fire demonstrates how complex industrial systems can shift from stable operation to emergency conditions within moments. A combination of fuel, heat, pressure, and structural exposure can allow a localized ignition to become a major fire. Investigators will determine the exact cause, but the event already underscores the importance of safety systems, monitoring, and rapid response in modern refineries. Incidents like this serve as reminders that industrial facilities require constant vigilance and continuous upgrades to minimize risk. If you found this explanation helpful, remember to share this video, like it, and subscribe for more clear and educational breakdowns of major global events.